Right, so now we will talk about adding and subtracting rational expressions. It's the exact same idea that we use for adding and subtracting fractions, but now we're talking about algebraic expressions. So in order to add or subtract rational expressions, we must ensure that all rational expressions have the same denominator, exactly as we did for fractions. We will learn how to find the LCM for algebraic expressions, then extend this idea to the addition and subtraction of rational expressions. It's a very simple process, but I just discussed it in a lot of depth because, as I've said repeatedly, under exam conditions we become frantic, we become anxious, and that's when we make stupid mistakes. So that's the reason why I will discuss it in such a way that you'll have a rigid formula that you can use to solve these questions, but it does not require so much of thinking. Right? So just if you keep practicing it, you'll become better at it, is what I'm saying. Remember that in order to find the LCM, we break each number into its prime numbers, and then we find the product of all shared and unshared prime numbers for each number. Exactly as we did here. I've discussed this extensively. I'm not going back into it. But we took all of the shared prime factors, or the prime numbers, and we multiplied them together. To find the LCM for algebraic expressions, we must first convert each expression into its simplest factors. By how? By factorization, which we've discussed extensively already. Then find the product of all common factors, your shared factors and unshared factors. So let's take an example here, right? If you're given x plus 2 and times x plus 1, and you're given x plus 2 all squared, to break x plus 2 times x plus 1 into its factors, it'll just be separated x plus 2 times x plus 1. To break x plus 2 all squared into its factors, it'll be x plus 2 times x plus 2. So then we can group our shared and unshared factors. See, x plus 2 is common to at least 2 of these numbers, so it becomes form parts of our shared. X plus 2 it has no other pair here, so it'll be unshared. And this x plus 1, it has no other pair, so it'll be unshared. So then we multiply our shared by our unshared. So it'll be 1 of this x plus 2 multiplied by x plus 2 and x plus 1. That'll give you x plus 2 all squared multiplied by x plus 1 all squared. So this here is the same as our LCD, right? So this is what we call the new denominator. Remember, there's all those rules that we learned under fractions. Same idea applied. Becomes the new denominator. Okay, right. So what does this mean? This is the lowest and common multiple that exists for each of these numbers. Meaning that each expression given, this one and this one, can divide evenly into this LCM without remainder. So it can divide evenly into the LCM without remainder. Okay, so it's the lowest and it can divide evenly into the LCM without remainder. Okay, so if we had 1 over x plus 2 times x plus 1, right, plus 1 over x plus 2 all squared, then the LCM will be x plus 2 all squared multiplied by x plus 1. So what's this? Your new denominator over the old denominator. We'll find out what factors are missing and multiply it by the numerator. So in this case here, x plus 2 is missing, so it'll be x plus 2 multiplied by 1 from there. Plus, here we'll find out what factors are missing. If you take this and divide it by that, this and that will cancel, so we'll have x plus 1. So it'll be x plus 1 multiplied by the 1 that's there, right? And then what we are left with? X plus 2 plus x plus 1 is 2x plus 3 over x plus 2 all squared, x plus 1. Very simple. That's how you solve the question. So it's very simple ideas. It's all the ideas that we learned from fractions, but we're just applying it to algebraic expressions. And let's look at a bit more. Another tricky example here. We have x squared and x plus 2 squared. So x can only be broken down into x. X squared, as we said under the LCM and HCF videos, can be broken down into x and x. And x plus 2 all squared can be broken down only into x plus 2 and x plus 2. This x and that x has a pair, so therefore we can group them. This x is on its own, so you can't. It'll be an unshared factor. This x plus 2 will be an unshared factor, and this x plus 2 will be an unshared factor. So it'll be your shared multiplied by your unshared. So it'll be 1x from there, multiplied by another x, multiplied by x plus 2, multiplied by x plus 2. So therefore we get x squared into x plus 2 all squared. So this is the lowest and common factor that exists for each. So this LCM is the lowest and common factor that exists for each of these terms. So if you take any of these terms and you divide it by here, you will have no remainder. It'll divide evenly into it, and that's what we wanted. So this here is like the LCD. It's the lowest number that is common to all of the numbers, right? And what this does is, when we simplify the fractions, it will get the simplest answer, because since this is the lowest, right? So we have 1 over x plus 1 over x squared plus 1 over x plus 2 all squared. Then this becomes a LCD. So therefore, you'll have x squared into x plus 2 all squared, and then you'll solve. Very, very simple ideas. It's like exactly as we did our LCM and HCF for fractions. Exact same idea. Okay, but there we worked with monomials. Now we're starting to bring in like binomials, different variables, different algebraic expressions, and so on. Alright, with this in mind, let's start discussing adding and subtracting rational expressions. So let's say we were given two fractions and we needed to add them together. We first have to ensure that their denominators are the same, and once the denominators are the same, we can add the numerators. So it'll be 1 plus 4, which will be 5 over 2. Now let's do this with rational expressions. Alright, so that was fractions. Now we're talking about rational expressions. If we were given 5 over x minus 1 all squared plus 2 over x plus 2, now if you look at these denominators, we have to find the LCD. X plus 2 has no common factor, x minus 1 has no common factor here, and x minus 1 has no common factor. So therefore we have no common factors, so we have to multiply all the unshared. So we have no shared, we have to multiply all the unshared. So therefore, it will be x minus 1 times x minus 1 times x plus 2. It will give us x minus 1 all squared times x plus 2. Now the LCD is the new denominator for both the fractions. If you read over the previous section where I discussed the implication of the equality sign, you would understand that each expression has to be an equivalent to the expression above it ends. We have to find a way to express each of these rational expressions with the new denominators, because only then are we able to add the rational expressions. Exactly as I talked about this extensively with fractions. I said this is the new denominator, so we have to find a way to re-express this fraction with this new denominator. And we have to find a way to re-express this fraction with this new denominator so that we can add them together. Right? I've already talked about that extensively under the fractions module. So we'll use a simple approach. We'll take the new denominator and divide it by the old denominator. So new denominator divided by old denominator, we get x plus 2. What do we do with this x plus 2? We multiply the numerator and denominator by x plus 2, which is effectively multiplying by 1. So we do not change the question. We're re-expressing it so that we can get the denominators to be the same. Right. Then we take the second fraction, rational expression number 2. It'll be this new denominator here over the old denominator, which will give us x minus 1 all squared. What do you do with this x minus 1 all squared? We multiply it by the rational expression number 2, and we multiply by x minus 1 all squared over x minus 1 all squared. Right, so if we do that, see if we did this for expression 1, you should get this as a result. As you can see that the x plus 2 are common factors in both the numerator and the denominator. This enables us to retain the equality of the expression, all the while re-expressing the rational expression using the LCD. Right, we do the exact same thing for rational expression number 2. If we multiply by that over that, we get this here as a result. So what we have now, if I have to just zoom out here for a second, right, you can see this. We have these two expressions here that have the same denominators, but we didn't change anything, we just re-expressed it. So now we can, what we did, we added them, so we can add them together. So basically now we're making use of the multiplicative identity and to retain the equality of the expression. This enables us to find a denominator that is common to both the rational expressions, and we retain the equality of the expression, everything that I've discussed so far. So we have this fraction, we have that fraction, right? Now since the denominators are the same, I can just add the numerator. So 5 into x plus 2, that's there, plus, which comes from the question, into 2 plus 2 times x minus 1 all squared. Right, we have that there already. Now what we can do, remember now, if this is a minus sign here, then what you'll have here is a minus sign. You have to be very careful here, because this minus sign here will distribute into the terms that's in the brackets. So you have to make sure that you copy whatever sign that you have there. If you're subtracting fractions, you'll subtract these two parts. If you're adding, you'll add these two parts. Very simple. So now if you have to open up the brackets and simplify, we'll have 5x plus 10x plus 2 into. We have two identical binomials that we're multiplying, so we'll employ SMS. Square the first term, 2 times the first term times the second term will be minus 2x. Square the last term, which become plus 1. Now we can distribute the 2 into the brackets there. So we'll have 2x squared minus 4x plus 2. And we'll have the 5x plus 10 from the top. Now we can add and subtract like terms. So it'll be 2x squared be 5x minus 4x is x, and 10 plus 2 will be 12, right? And that's how you'll simplify that question, adding them together. So if you multiply the first term by the last term, you get plus 24. The factors of plus 24 is 1 and 24, 2 and 12, 3 and 8, and 4 and 6. Now, since you have a positive last term, you will either have two positive terms or two negative terms. But since you have a positive middle term, you'll need to have two positives. So if you add these two terms together, 1 plus 24 gives you 25. 2 plus 12 gives you 14. 3 plus 8 gives you 11. 4 plus 6 gives you what? 10. So there's no way that you can get a middle term when adding these two factors together that will give you 1. So therefore you cannot factorize it. That's what it means. You cannot factorize it. And if you put it in your calculator, you'll get a I. What that I means is that you're getting a non-real solution. It's an imaginary number. See, non-real, remember you said non-real / imaginary numbers, it's the exact same thing. This I means imaginary, so therefore you'll have no solution, therefore you cannot simplify that. Okay, if you put it in your calculator. So therefore this is solved fully, but we have to state our restrictions here. So it'll be, well, not necessarily, because you didn't cancel anything. Think about that, you didn't cancel any factors, so you don't have to actually have to state any restrictions because you kept the denominators the same at the top and the bottom. Think about that. But if you want to be a bit more technical with your maths, will say x minus 1 all squared is equal to 0. So x minus 1 is equal to 0, therefore x is equal to 1. X plus 2 is equal to 0, therefore x is equal to minus 2. So at x equal to 1 and x equal to minus 2, this rational expression will have no solution, because at these points here, the denominators will be 0. Understood? Right, so that's a very long process. To solve it using the methods that we use, which is very long. Exactly as we did with HCF, I gave you 3 approaches. I said HCF, we did the definitions approach, we did the prime factorization approach, and lastly we did what? We did definitions, prime factorization, and we did by inspection, isn't it? So now we'll do the exact same thing here. For LCM, I already did the definitions approach, already did the prime factorization approach. Now let's do the by inspection approach. Right, by inspection. So how would you do that? Let's say let's take an example here, right? Let's do an example. Yeah, let's say you have 1 over x minus 1 all squared plus 1 over x plus 2 plus 1 over x minus 1 all to the power 4. How would you do this? First, we factorize each denominator. Do I need to factorize anything here? No. So therefore, we already have it factorized. That's done. Then you write the different factors that appear. So let's look at these three. Which factors are different here? See, this x minus 1 and that x minus 1 is the same. They have x minus 1 and x minus 1 here. What's different? This x plus 2. So therefore, the first thing that I'll write is all the different factors. So x plus 2 is the different factor. Then you'll find a factor that appears more than once in the rational expression. Oh, so then I see the x minus 1 appears here and here. It appears more than once. You will choose the factor from the rational expression that has the highest exponent. So therefore, which one has the highest? X minus 1 to the power 4. And therefore, now I have the LCD. So remember when we did with the HCF, we took the number that had the lowest exponent. Now when you're doing LCM, we take the one that has the highest exponent. Go back, compare these two LCM and HCF done by inspection. Please do this for me so that you'll understand how to apply yourself in these two different scenarios. Be very careful. It gets a bit counterintuitive if you're doing it by inspection, but I'm teaching you how to work fast in maths. So you need to know. For LCM, if the factor appears more than once, take the one that has the highest exponent. This factor and that factor appeared more than once, I took the one with the higher exponent. When you did HCF, you'll take the one that has the lower exponent if it appears more than once. So I would have taken this if I did HCF. Understood? All right, let's do another example. Let's say that we got, let's take this exact example here. Let's say we have 1 over x minus 1 all squared plus 1 over x plus 2 plus 1 over x minus 1 to the power 4 times x plus 3. Right? So basically, the first thing we do is factorize, right? It's already factorized. Then we find out what's different. See, x minus 1, x plus 2, x minus 1, x plus 3. Don't worry about the exponent for now. Just look at the factors. This and this is common, so don't worry about that because we'll use step 3 to solve that. But the x plus 2 and the x plus 3 is different. So far we have x plus 2 and x plus 3. Then since that and that is common between the two fractions, take the one with the higher exponent. It'll be x minus 1 to the power 4. And that's how you solve the question. Now, when I first did this, I never used the inspections approach because I found it very counterintuitive. I couldn't understand it. But for now, if you want to use the long approach until you fully convince yourself that this is the way to go, do it. Understood? Right, so yeah, so that's basically how we do that, and you basically understand everything that you need to know for rational expressions. Very, very simple, very simple. Just master fractions and master factorization and you'll be able to solve these questions. This is why I stress those sections so much. This is why I spend so much of time doing those sections, because it applies in so many other sections. Okay, and remember your restrictions. Again, dividing by 0, everything under the square root or even root has to be positive, and the log of a negative number. Please go over that again. Okay, very, very simple.